So hello, everyone. Thank you for coming to this second session of the day. Today is the first of two lectures. I'll just remind you of the rules. The first lecture today is 90 minutes long, and you may use the chat window to ask questions. Please type your questions. Please mark if it's urgent. If necessary, I'll ask Ali to answer the questions. We can answer a few questions at the end too. Tomorrow lecture will be a little bit shorter, and there will be also a lot of time for discussion after it. But please, in any case, do not at all censor yourself for asking questions today. Put as many questions as you want in the chat window. If we cannot look at all of them today, I'll just make a copy and send them to Ali. So with that, it's a real pleasure for me, and it's a privilege for us to introduce to you Ali Yazdani. He is one of the world leaders on quantum material research. So I looked at his record, and he's the class of 1909 professor of physics in Princeton. And I wrote to him yesterday, what's that class of 1909? And this just shows you how Princeton alumni are proud of their places. It's the class of 1909 that put an endowment for financing a professorship for the future. So he is that professor today. His training was basically on the other side of the country, in the West Coast, in California, in Berkeley and Stanford. And Ali, I think you were a grad student of Aaron Kaptonik, right?
That's right.
Okay, that's it. And had a postdoc in Almaden, and had appointments in very prestigious universities. I met him first, I think, in Illinois at Urbana-Champaign, and then he had an appointment in Stanford, and then in Princeton, where he is the director for the Center of Complex Materials. I could spend all the time of his talk just by telling his achievements and honors. I think it suffices to say that last year he was elected for the National Academy of Sciences, which is an extremely prestigious recognition for his. He's a world-class scientist in the low temperature physics of quantum materials, as we call them now. He has a fantastic STM lab in Princeton, where he produces fantastic science. But to make even more jealous, you have an example here, fabulous images that we cannot produce. My images are in infrared, nobody sees them. So we are always envious of his fantastic images that he has from his data, make covers of many magazines and journals. He's gonna talk today about Majorana fermions, I think, as he told me, and tomorrow it will be twisted bilayer graphene that you should be experts by now with all the content you saw in this school. So without further ado, please, Ali, take it away. And I'll give you a warning maybe at 15 minutes before the end of the hour and a half, if it's okay with you.
Yeah, thank you. Okay. Well, thanks very much, Ricardo. It's a great pleasure to talk to you today. It's a shame that we can't be in the mountain in Les Houches, which is a beautiful place. So maybe in the near future. So as Ricardo mentioned, I'm going to devote today's talk to talk about Majorana fermions. And as he also mentioned, I'm happy to answer questions as we go along. And tomorrow I'll talk about a completely different topic. I figured you guys had heard enough about twisted bilayer. You could use a break for a day, and then we can go back to that exciting field as well. So my talk today is about how we have found a way to create Majorana fermions in actually two different condensed matter systems. So I'm going to start the talk by telling you why we're so excited about these quasi-particles and what the sort of background is in the field, and then go into some details of several different experiments in which we've used the scanning tunneling microscope to both visualize and test the presence of Majorana fermions. So before I get started, let me tell you the team that's been working on this problem in my lab. Currently, the work in my lab on this topic is led by Berthold and Hao and Ewan, and we collaborate very strongly with Andre Bernovic and his group over the years. And of course, this is a topic that's been going on in my lab for 5 or 6 years. So a number of people, Younglong, Sangjong, Maleka, and Ben, and also collaborating with Alan have been sort of the critical thing for us to develop all these experiments and the different measurements. So let me just start by reminding you that Majorana basically introduced the idea of real fermions by looking at the Dirac equation, and which was developed to describe complex fermions, to propose that there could be elementary particles that are neutral spin-and-a-half particles. And the novelty of this idea is that this would be a particle that is its own antiparticle. So as you might know, our colleagues are looking for such elementary particles, if you like, in the vacuum. But as condensed matter physicists, what we are interested in is to take concepts from any area of physics and realize them in quantum materials. So what we have in many condensed matter systems is that the thing that's easily available to us, like electrons, are the usual Dirac fermions. And we want to engineer ways in which we could create a real fermion, which would be this Majorana fermion. And so, of course, how would you go about doing this? A simple way to think about how you would do this is if you want to make a real number and you're only given complex numbers, you just have to add the complex numbers in the right way together to get the real number. So you can think about electrons and holes as complex fermions that we have in solids, and how a judicious sort of addition of them together would allow us to create Majoranas. Now, so this idea of mixing electron and holes is something that brings us very quickly to superconductivity. The idea that in a superconductor you have Cooper pairs, and the idea that you can take an electron and inject it into a superconductor, and the only way it can get in is if a hole reflects back, and you can get Cooper pairs going forward. So this is the idea of Andreev reflection. So in fact, if you think about this mixing of electrons and holes, as many of you are familiar, we introduced these Bogoliubov quasi-particles, which are mixtures of electrons and holes. They are neutral fermions in order to actually diagonalize the BCS Hamiltonian. So the concept of Majorana is very natural to think about in superconductivity. But of course, this idea was sort of really accelerated forward by the proposal from Alexei Kitaev of a simple model Hamiltonian, one of many of the novel Kitaev Hamiltonians, in which you think about a simple one-dimensional system in which you have electrons that you have somehow stripped them of their spins. These are spinless electrons. And you think about pairing of electrons in this one-dimensional chain of sites. So of course, once you get rid of spin, you cannot put the two electrons pairing on the same site. So you will end up, the sort of simplest model you can have is you can have electrons pairing in what we call the P-wave channel, pairing on nearest neighbor sites because they can't occupy the same quantum state. And he considered in this very simple model of hopping T of these spinless electrons, this pairing that I just introduced, and the chemical potential. And he recognized that this simple Hamiltonian has basically two phases that are both superconducting. Now, to distinguish these two phases from one another, you have to think about its topological property. Its topological property is such that as you tune the chemical potential U, mu, or T, or delta, you can go between one phase to the other, a trivial phase or a topological one. And as you know, many topological phases can be recognized by their corresponding boundary mode, which is created because when you cut the system in half, you have to sort of remain topological. And it knows the difference between its inside and its outside. So a topological gap closes, it goes to 0, and it opens into another trivial gap, and that's what stabilizes a 0 mode at the edge of such a system. Now, what you have here is a kind of a very exciting idea in which you have this edge mode. And the way Alexei realized this is he introduced the notion of taking your complex fermions and breaking them up into real Majorana operators, and which is the natural way of diagonalizing this Hamiltonian. And these 0 modes, you can kind of think about them as a pair of Majoranas that are localized on either end of a topological superconducting wire, in which you have basically taken an electron, if you wish, or quasi-particle and split it in half. So they represent the same quantum state. So it's important to think about it this way because you can kind of think about if you were to occupy this Majorana state by an electron, this electron will live sort of at both ends. And if you combine them, if you fuse these two Majoranas together, you would either end up with one electron or no electron at all. And this is kind of a very novel property of these Majorana end modes. So the fact that they come in pairs, which is different than what Majorana envisioned as elementary particles in this condensed matter system, is one which gives it sort of the exotic property that you can create entanglement by braiding. So we think about exchanging or taking particles around one another and picking up a phase from the exchange of particles, for fermions and bosons. And here you have the added feature, which is that depending on how you take this object around the other one, as is illustrated here, which we call braiding, you can create different sort of degrees of freedom, which is what people are excited about in order to code information and do computation. So I'm not going to talk about this theoretically, I'm going to talk about it experimentally, but let me just say that our theoretical colleagues have come up with many fantastic ways of thinking about doing this manipulation and braiding and so on. And this is kind of what is driving a lot of the experimental effort to not only realize this Majorana zero mode, but find ways in which you can manipulate them and braid them. Okay, so that's the backdrop for the theoretically. Now, how would you go about making such a topological superconductor? So thinking back to Kitaev's model, what you're thinking about are spinless electrons. So how do you make spinless electrons? So the first idea that sort of was put forward by Fu and Kane was that to think about the topological boundary modes of a two-dimensional topological insulator. So these are systems which spin of the electron and its momentum are locked together. So this is a system that's insulating in its bulk, but it has boundary states very much like our Majoranas here, but created because of the presence of spin-orbit coupling and an inversion of the gap in the bulk, and then the gap in the vacuum being different, creating these edge modes. And these are protected by time reversal symmetry in for example, 2DTI. And this idea was to proximatize these edge modes. And actually, I'm going to talk about this today. It's an experiment we have done recently. And soon after that, it was proposed that maybe we don't need a TI. Maybe we can take a semiconducting nanowire, which has a very strong spin-orbit coupling. And with the application of a magnetic field, this Rashba split 1D band can be gapped here at the gamma point. And basically now you have the forward moving electron having spin up and backward moving electron having spin down. And this is sort of, in a sense, what you're looking for in terms of trying to make a spinless system. So the idea was if you proximatize this, you could get Majorana zero mode. So I'll say something about that platform in a minute, but what my group and I focused on in this field was to try to find alternative to these platforms. And one of the things I will speak about at the beginning is how we use magnetism and superconductivity to try to create the condition for a Kitaev chain. So this is sort of basically illustrate the Fu and Kane idea. You have these topological edge modes, and basically whenever you have these topological surface states or edge modes, spin and momentum are locked, and it gives you sort of this condition that you will have to make a topological gap because you no longer have the spin degree of freedom as one you can play with. Now, as you know, the experimentalists in Delft and many other places, in Copenhagen in particular, they basically went off and made exactly this platform with semiconducting nanowire that's proximatized, and you apply a field to create the gap. And the way these experiments detect the presence of Majorana zero mode is by doing a tunneling spectroscopy. And they do tunneling spectroscopy from this normal electrode tunneling into the edge of this system where you would expect the Majorana to be. So this got started from Leo Cohenhoven's group, and it's been going on. And you know, the status of these zero bias peaks is a field that is somewhat problematic. If you look at the literature, after 8 years, there's still papers with titles of the good, the bad, and the ugly. And these are things that, you know, even the originators of the experiments are really looking into. And the key idea and the problem here is you can have Andreev states masking as Majoranas. And the reasons for that could be manifold, which I will not get into. So even from the beginning, when these devices were made, my group's interest was that, well, how do you really know if this zero bias peak is coming from the end of this device? So this is why we started thinking about creating situations which you can use the scanning tunneling microscope, and also in particular, the role of disorder. Okay, so let me just briefly tell you about this platform that we created and how it works. So our group and many others, as well as building on work of some of the people before us, which consider magnetism superconductivity, we came up with the idea that you could have chain of magnetic atoms on a surface of a superconductor. Well, how would this work? The first part of my talk is going to be on how this works. I'm going to just do a brief review of all the results because they're a few years old, but I'm going to focus on this question of how do we really know that these are Majorana zero modes from spin polarized STM experiments. And then once I do that, then I'm going to go back actually to the topic that sort of got this field started, which is topological edge mode, and tell you about a more recent experiment, which is how we actually realize this other platform, which also lends itself to STM studies. Okay, so at the first look, you can kind of think about Kitaev's model of sites in which you have pairing, and think about if you had a superconductor and placed on top of it a chain of magnetic atoms, which these magnetic atoms had their sort of spins be non-collinear. So if this is in contact, this is kind of how we sort of started thinking about this idea. If you think about pairing from a superconductor underneath, well, a Cooper pairs, you wouldn't really want to jump onto this site if the Cooper pairs that you're using are singlet, but you can kind of think of approximately as misalignment with the spins actually gives you the probability to have pairing on nearest neighbor sites. So this is kind of the sort of the simplest way of understanding this. But now you can do a more sophisticated thinking about the band structure of these ferromagnetic chains. Incidentally, there is a way in which you can think about these magnetic atoms as also being atoms in which they introduce in-gap state into the superconductor. These are called Shiba states. That's a different perspective to think about this system, and it actually arrives at similar results. But this one is perhaps a little bit easier if you don't think about when the atoms are far apart from one another, but they're close enough that they make their own one-dimensional bands, just like you would have a chain of free hanging, iron atoms, if you could make such a thing. So if you had strong enough magnetism, what will happen is you just get spin split bands. And if you have the conditions such that you have, let's say, one band, or in particular odd number of bands crossing the Fermi level, what you would have in a situation where J is large is you will have one band with a very strong spin orientation or spin polarization. So this is our minority band, if you will, if you're thinking about this chain as just magnetic. Now, the nice thing about this platform is that as soon as you bring in some superconductivity to put in contact with this system, and you think about spin-orbit coupling in the substrate, you can begin to think how the system can become a Kitaev model and a topological superconductor. So what's the basic idea? The basic idea is that if you think about the electrons at the Fermi level here being spin polarized, and their spin being up, if you have spin-orbit coupling, it would just, the orientation of these spins can be slightly canted relative to one another at the Fermi level because of the spin-orbit coupling. And that angle of canting is enough for you to proximitize this one-dimensional band with a S-wave superconductor which has singlet pairs. Now, the magnitude of that P wave or topological pairing gap is going to depend on the ratio between the spin-orbit coupling and the exchange interaction J, which is the level of the polarization of these bands that you see in this diagram. Now, the advantage of this system compared to, say, nanowire system is that as soon as you get any kind of superconductivity introduced in this system, if the spin-orbit coupling is large enough, it is very likely to be topological. So the phase diagram of this system as a function of, say, parameters J or the chemical potential, it has very large topological phases, which you can access if you think about J being large enough. So the disadvantage, of course, is that even though no fine tuning is required, tuning is very difficult. And this is something that is a disadvantage of this system compared to the nanowires, in which you can tune the chemical potential because there are semiconductors. But our purpose for this experiment was first to actually see if there are such Majorana zero modes before thinking about how you can manipulate them. So we've done this experiment a few years ago. Let me just briefly tell you how they worked. You use iron on top of lead. Lead has strong spin-orbit coupling. You evaporate iron on the lead surface and you anneal it. And these iron atoms basically can go in between the grooves of this particular lead surface, which is lead 110, and it creates a one-dimensional chain of iron atoms. We could, using spin polarized STM, which is a technique I'll introduce in a moment, more detail, we can show that these iron atoms chains are actually ferromagnetic because we can flip the magnetization of the tip and get imaging contrast, which toggles back and forth. We could also measure the band structure of these chains in terms of its spectroscopy and sort of confirm that we have a situation where we have something that looks like a crossing of a band if you compare it to theoretical calculation, which is a minority band. But more importantly, what we did in these experiments was when we did spectroscopy, so here's the tunneling spectroscopy measured at 1 Kelvin on the lead substrate with these iron chains. And the chains you can see, this is the two ends of the same chain. And what you see here is when you put your tip on the substrate, you see the superconducting gap of the substrate. When you put your tip in the middle, you get an incomplete gap. You get these big peaks which lie at energies below the energy gap of the substrate. These are called Shiba states, or here there will be a band of Shiba states which are introduced by the magnetism of iron into the lead. And you can see that there is a zero bias peak that appears when you put your tip at the location of the stars at the two ends of this chain. Now, you can take data not just as one or two location, but you can take data as a function of location. And the color here represents the strength of the tunneling signal. And what you see here is this feature here up here, and this feature down there are basically the zero bias peak that's probed in this experiment. So this immediately tells you the power of this STM technique. It shows you that indeed there is a localized state living at the edge. Not only you know it's in its energy, which is zero, but also in this plot where this axis is energy and this axis is distance and the colors is the density of state, you see that they are localized and a very few, about a nanometer region at the very end of this chain. So that chain, yeah, go ahead.
There is a question here from Yang Gao. Why does the coherent peak disappears?
So you mean on the wire?
Gao, do you want to turn on your microphone and ask the question?
Please.
Yes, can you hear me? Yes, why on bulk and at the end I see the coherent peak disappear?
Yep. You're talking about these peaks. Well, basically what happens is that in the wire, you will have a number of in-gap states. So if you simulate this in the model calculation, you find that even though you can see that there is a region of energy here, which marks the edge of the gap, if you wish, there is a spectral weight transferred between the edges of the gap, the states at the edge, into the states inside the gap, which are these Shiba states. So this is quite typical of what you get in the tunneling density of state, even if you tunnel near an individual magnetic atom, is you will see a spectral wave transferred from the coherence peak to create the states in the gap. And here we have a large number of in-gap states, which are these Shiba states. Good question. Okay, so we extended these experiments that were first done at 1 Kelvin to millikelvins, which gave us a lot more energy resolution. And here is a measurement which kind of relates to the question that was just asked, with very high energy and spatial resolution. And you can see these are the coherence peaks of the superconductor, but you can still see the gap in the signal that we know is there from superconductivity. But this gap has a lot of in-gap states. You can see all these features inside, which are created by the magnetism of the chain. And this thing in the middle here is our zero bias peak, which in this experiment then we could show to have basically resolution comparable to the temperature of the electrons in this experiment, which was 150 millikelvin. So we really know this is a zero bias peak. We know that it is living exactly at the edge of these chains. We also actually could do an experiment in which we could measure its electron and hole content. So these type of typical STM experiments are done using normal tips for the STM tips, which measure the tunneling density of states as a function of bias. But you could use superconducting tips. So remember, to tunnel into a superconductor, you need to overcome its gap. When you tunnel between a superconducting tip and a superconducting sample, you have to overcome the gap of the tip and the gap of the sample. And what you can do is you can use this sort of positive voltage and negative voltage tunneling from a superconducting tip to measure the electron and hole component of the in-gap states separately. So what's plotted here is such a measurement with a superconducting tip. The purple and the Kion curves are the positive and the negative side. And what you see here is that the peak, which is at 0, has exactly sort of a content, which is half electron and half hole, which is what you would expect. The two lie on top of one another. But the states that go away from this 0 are electron hole asymmetric. And they have different electron and hole content. So you can distinguish these zero energy states also in this particular way. Now, so these experiments have been reproduced by a number of different groups in this system. And also there is another study of iron atoms on top of rhenium, which showed indication of Majorana zero mode being there as well. But the question we asked is, okay, these all look good. It follows what you expect theoretically. There are a lot of reason to believe that this is Majorana zero mode. But is it possible to do an experiment to be sure that this zero bias peak is not an accidental trivial localized state at the edge of our chain? In fact, this is has been the problem with this field from the beginning, which is that you see a zero bias peak. There are lots of ways to get zero bias peaks. If you can even prove they're at the end, which we can easily do in this experiment, as you just saw, people could always say, well, maybe the potential at the end was just somehow adjusted just to tune a Andreev state or a Shiba state in this case, which we are looking on the atomic scale, to be pulled to zero energy. And it turns out there is an experiment you can do. And that has to do with the spin signature of the Majorana. So remember, Majorana is its own antiparticle. So whenever you write up the operator for it, you have the conjugate has to be equal to itself. So we make this Majorana out of spins that are attached to electrons as well. So Majorana has a spin in our problem, and it is kind of a contrast between this Majorana and a typical Bogoliubov quasiparticle, which leads to a way to distinguish them from a trivial Bogoliubov quasiparticle that is living at zero energy. Because if you don't put the spin to be the same under these guys, the conjugate is not going to be equal to itself. And the typical Bogoliubov quasiparticle is made out of a spin-up electron and spin-down hole, which, as I will show you, relates to the spin polarization of the background material from which you create your Bogoliubov quasi-particle. So let me go back and talk a little bit about these in-gap states, which is gets created when you put magnetism in a superconductor. So we have the gap of a superconductor, and even if you put a single magnetic impurity, you would get in-gap states because the J dot S of the impurity with the S of the electrons is a perturbation which is breaking time reversal symmetry, and this creates in-gap states in the superconductor. This was first shown by Yu, Shiba, and Rosinov. And the energy of these states depends on the strength of that interaction between the superconductor and the spin. But now let's think about the spin of these in-gap states. Where does that spin come from? Okay, so you can think of it, let's see. Yeah, so this is the spin polarization of these in-gap states. So of course, if I had the magnetic impurity to begin with, sorry, this slide is going backward. The left should come on first. How do we get a magnetic impurity to begin with? Well, we have a partially filled, let's say, d band, d orbital, and this is what gives us magnetism to begin with. So a way to think about our magnetic atom from like the Anderson model is to think about the d orbital, which is you've got the sort of the down orbital filled and the up electron is empty. And of course, this orbital has some width because you've put this magnetic atom on the surface of a superconductor. So there is sort of the polarization, if you wish, of the electrons at the Fermi energy is determined by the ratio of these two peaks, which is zoomed in here on the right-hand side. So if I zoom in, remember, these energy scales are very large. They're atomic orbital energy scale. Hybridization is of the electron volt scale when you think about atomic orbital hybridizing with the metallic states. But what we are doing is superconductivity. We are looking at milli-electron volts. So this background difference here is the difference that makes that site magnetic. And it's actually the in-gap states inherent their spin polarization from the background normal state. So if you turn off superconductivity here, you will have no gap. The blue curve will be larger than the red curve. Okay, it actually comes from, the polarization comes from the spin minority band from the top part. And the height of these peaks, the asymmetry of these peaks is actually relates to the asymmetry in the polarization that makes this site magnetic to begin with. It can also be changed if you add another potential, but the key thing here is that the asymmetry reflects this spin polarization. So if you could measure the spin content of these states, which are fully polarized, so this state is fully polarized up, this state is fully polarized down, but the ratio of their density of states would be the ratio of the normal state density of states. Now, how do we make such measurements? With using the STM. So you use STMs where you have the end of the tip with a magnetic atom at the end, usually a small cluster, because you don't want the magnetization to be from the tip create fields that perturb superconductivity. So we use very small clusters of, let's say, iron at the end of the tip or so on. And in one of our instruments where we can do these experiments, this is done at 1 Kelvin, we have a vector magnetic field with which we can train the orientation of this spin at the end of the tip, which allows you to measure polarization along at least up and down direction, even though you can polarize this direction, and the polarization direction depends not just on the magnetic field, but also the anisotropy that's locally present there, but you can at least flip it between the two different orientation. Now, it turns out that STM does something for us which gives us a key advantage in order to distinguish this zero bias peak Majorana zero mode and the Shiba states if they accidentally go to zero energy. And that has to do with the way the STM operates, which is to keep a tunneling current constant. And that's how we typically take an STM image. And even we where we park the position of the tip to take a spectra, which we open the feedback loop of the STM, the height of the tip above the surface is determined by that stabilization of the tunneling current to give you a fixed current. So what does that mean? That means that if I, in this context, let's say this is my magnetic chain, and these magnetic chains have very strong spin anisotropy. It's very difficult to flip their magnetization. But we can make tips where it takes very small fields, like less than a Tesla or 250.2 Tesla to flip their magnetization. And we can do that and then remove the magnetic field. And we can just measure the height of the island. In this case, the height of the chain. And what you see is the height is slightly different. And this is a reproducible effect. You can see there is structure on these chains and it appears at a slightly different height. And what this is telling you is that what the STM did is because the spin density of state, the normal spin density of state is sensitive to which orientation is your tip, you have basically canceled, you asked for the same current in these two experiments. So your tip adjusts its height to a slightly different value to give you the same basically tunneling current. So this is basically canceling the difference in the normal state density of state, which is coming from spin polarization. And a way to see that, so this is another example. This is for a different chain. This chain is, magnetization is opposite to the other one. So you see the red line measured with the tip, let's say up, was different than the tip down and vice versa. Now, what the importance is that if you now look at the normal states, remove superconductivity completely, and repeat this experiment on the chain where you flip the magnetization of your tip, you see these two different heights in the topography. But then if you do spectroscopy with the tip that's spin up and a tip that's spin down over this narrow energy window near the Fermi energy, you get the curve that's exactly the same. But of course, we know this is magnetic. We see the magnetization here in the height. So what happened to the spin polarized density of state? Well, you just canceled it. You got rid of it. And the cancellation is evident here by the raw data. Of course, you can go back and say, oh, these two curves were measured at slightly different heights. So I'm going to normalize them because this is, although the conductance is the same, the tunneling gap is different. And if you do that, you will convince yourself that there is about 13% polarization due to the presence of iron there in the magnetic signal that you measure. And this is quite typical of what you would expect if you think about spin polarized density of state of iron at the chemical potential. So how does this work for us in this context? So what works for us is the following, is now we go theoretically and think about these in-gap states, trivial in-gap states, which are created inside the gap of the superconductor because of the presence of magnetism. As I told you, these are spin up and spin down states. And if you think about tunneling into these states with a spin polarized tip, of course, what you would find is that there would be some sensitivity on whether your tip is up or down. And if you make a measurement with the tip up, you get one contrast. You see here the red curve is up, and this red curve is below here. And then if you flip the polarization, the blue curve is up and the blue curve is down here. Now, what you can do is you can say, oh, let's compute the spin polarization, which is looking at the difference between these two curves. So what's interesting about this measurement is that it has this asymmetric behavior as a function of energy, which means what? Which means that if these in-gap states are created by this typical mechanism of in-gap states and magnetism, as you bring the in-gap states closer and closer to zero energy, the difference in this measurement goes to zero. And the reason this is going to zero is because we have kept the tunneling current constant. So these theoretically produced curve here on the left are produced not just by the density of state, but keeping in mind that the STM does this cancellation in its typical measurement. So this is kind of what's kind of becomes an exciting thing, which is that if you had an accidental zero bias peak, in this measurement of polarization measured with keeping the coloring current constant, you should see zero contrast. Okay, so this is what you would get for a trivial state. This is what you expect. But what do you get if you had a Majorana? Let me see if I can, yes. So here's a calculation, another theory calculation, which is not done not for a single site, but for a chain. And this chain has, of course, in-gap states in the middle of it, just like you saw from the experiment, but it also has a Majorana zero mode at the end. What these calculations are the same calculation I showed on the last slide, which are experiments that show basically polarization measurement with the tip polarized up and the tip polarized down, measured under the same tunneling condition. And it has this asymmetric behavior that I told you about on the last slide, with it going through zero for the typical Shiba state, because the normal state density of state is, if you like, canceled. But wait, there is a zero bias peak, and it's not canceled if it's a Majorana. So the question is, where does this come from? Why does the Majorana zero bias peak has a different spin property than the Shiba state? So I told you at the beginning, at least sort of approximately, you would expect them to be different than these in-gap Bogoliubov states that are trivial. But let's dig a little bit deeper into this. Where does the spin of Majorana comes from? Going back to the model that I put for you, how we get these Majorana states is we think about this magnetism of this chain, creating this magnetized band. And you think about introducing superconductivity in this band if you have some spin orbit coupling. So how do you think about superconductivity? You think about superconductivity as taking this band and making its whole equivalent, flipping it, and then think about pairing, which opens up a gap here. So it opens up a gap, but what happens is that gap is topological. So at the edge of the system, there will be a zero mode, which is the Majorana, which comes from this particular crossing of these bands. And the spin property of the Majorana comes exactly from the spin property of this band, which is modified by the presence of spin orbit coupling. And this is kind of what's interesting about this, is that the fact that this Majorana zero mode peak survives, it has to do with the fact that it inherits its spin property from this zero crossing. Whereas if you think about the trivial states, they inherit their spin properties from not just this band, but also the spin properties from this band, if you like, because there is some probability that you would have polarization at this energy in the other direction. So this is why the Majorana zero mode is because of the topological property of this band, its spin survives in this experiment, as these model calculations show. So let's go to the experiment. So this is actually a very difficult experiment. So you make these chains, and this is sort of a cross-section cut of the chain, which you can see is this topograph. This is the substrate. You climb on to the chain, goes down. These are tunneling spectra. This is the raw data measured with the spin up and spin down. So you can sort of see the background superconductor gap. And then you can kind of see as you come onto the chain, there are in-gap states like we talked about. And then there is a zero bias peak here, which we are interested in. So what you have to do in this experiment is polarize your tip along, say, some direction shown by this green arrow, complete this measurement, which can take several hours, flip the magnetization, repeat the same measurement to obtain the information with opposite spin polarization measured under the same tunneling current condition, and then flip it back to make sure that the tip didn't change as you go and look at the same data measured now with the tip flipped back to its original condition. It takes a lot of effort to make sure that goes smoothly and you have enough data to say something, but you can really see that there are differences here, and these differences are reproducible. So you can see that—
Ali, it's Ricardo here. Just a naive question. you see the superconducting gap of lead disappearing when you go down just because you don't probe that deep in the system, or is there something more fundamental?
You mean this gap?
Well, in your top figure, you have, yeah, the big gap, the big bulk.
Yeah, so
Yeah.
the way to think about it is this was related to the question that was asked, which is to think about this data. It's there. It's just you have to have enough resolution. And that becomes very obvious when you look at the resolution at the lowest temperature. So you see this is a gap edge. It's still there. Do you see it? It's just when it's filled with in-gap states, which these wires do create, in addition to the Majorana, then the broadening of these things would make it hard for you to resolve the gap edge. Does that make clear?
Yeah, no, it's clear. Thank you.
Okay, so let's see. Right. But this measurement is done at 1.4 Kelvin, which this gap edge becomes harder to discern in data because of this broadening of these peaks. But what we are interested in here is the spin polarization of the measurement, which is clearly obvious in the raw data, from which we can construct this polarization by subtracting them and dividing them by their sum. So here's what the raw data looks like when you put the tip where the Majorana zero mode is evident. You can clearly see that there is polarization difference of this peak at zero bias peak. And you can construct this thing. And as I mentioned, these are very challenging experiments. So you have to make a measurement, make the other measurement, and go back and then compare two data sets, line them up and subtract them. And you can see the contrast in the raw data very clearly. And their noisiness in this comes from just getting exactly the same spot. But you can see that the in-gap states that live at energies higher than zero, they have this sort of asymmetric behavior. It's high here and low here. Whereas Majorana zero mode has picked a particular direction, which is what we call, let's call it up here with this particular tip. Incidentally, you can go look at other tips and you can find this peak to be down on the other direction because the magnetization of these chains and how they interact can be up or down, flips the magnetization of this in-gap state and flips the asymmetry of even these things when it's created. But that data is also in the paper. And here, same measurement where you have no zero bias peak, but you can still see the same Shiba states that you can resolve at the end, again having a asymmetric behavior. The contrast here on the lower side is hard to see, but you can see it in the raw data. So this is precisely what we are looking for, is a signature, which is, you can kind of almost intuitively understand it. This goes up and this goes down. When it goes to zero, this will be nulled. So where is this coming from? And this is basically the idea that we have, is that this can only come from something that is not a in-gap Shiba state that gets created with this process that we are very familiar with. So I think this sort of completes the set of experiments we could do to characterize these iron chains on lead, the zero bias peak themselves, pushing them to the lowest temperature, their electron hole symmetry, and also their spin signature all seem consistent with what we expect theoretically in the system. But of course, what our aim in the future is to create other kinds of atomic chains in which we can control the presence or absence of the Majorana in these chains in a more sort of toggled way or on and off way. And that's sort of where we are headed. But now I want to switch gears and talk about this other platform of edge modes proximatized. So maybe I should stop here and see if there are any questions on this part of the talk, and before I move on to the other experiments.
Anybody has a question on this?
Okay.
Well, we'll just move on.
Let me keep going. Very good. Okay. So we go back to Fu and Kane and many others who thought about topological insulators, edge modes, and how you would make superconductivity out of them. And the idea is similar to, it's what inspired the semiconductor nanowires. You proximatize these edge modes, and they will have a gap. But remember, these edge modes are topological, so they don't have an end. So in order to end them, if you wish, you have to introduce another kind of gap. And the other kind of gap you have to introduce is due to magnetism. So magnetism opens up a gap in these edge modes. It gaps the Dirac point. And in this gapping of the Dirac point, at this precise location where the magnitude of the gap from the Dirac point for magnetism and gap from superconductivity are exactly the same, is when you would get a zero energy mode develop in the system. Now, the advantage of this system is that, well, you don't need any overall magnetism. You know, the magnetism here serves a different purpose than the previous experiment. There, you know, where you have the Majorana zero mode, you still have magnetism in the system. And that's going to create a very interesting connection between how the spin in this system will present itself, as you'll see. And also, these edge modes are topological. So if you have some sort of a bend, they should just go around, right? And maybe the thing that's also exciting about this is that the gapping of the magnetism of this edge mode depends on the orientation between the magnetism direction and the spin of the edge modes. So if the magnetization direction is along the direction where these edge modes are polarized, then it doesn't do anything to them. It just lifts them up in energy or lifts this down in energy. It doesn't open up a gap. Where if it's perpendicular to them, is when you gap it with magnetism, the direct properties of these edge modes, and that's when Majorana will show up. So it's a nice experiment because if you could do it, then you could try to also validate that you have Majoranas if you find that you can switch the magnetization or make cluster or make systems with different magnetization orientation. So we stumbled upon the idea of using Bismuth for these experiments. And let me just remind you, Bismuth, bilayers of Bismuth, you know, original proposal from Kane and Millet for topological insulators was, of course, graphene with strong spin-orbit coupling, which is hard to achieve until other systems came along. But Bismuth bilayers, if you look at them from the top, they just look like graphene, except with very large spin-orbit coupling. And this large spin-orbit coupling basically creates for you the possibility of having a topological insulator if you could make bilayers of bismuth. This goes back to the work of Murakami, which introduced this platform quite soon after Kane and Millet for another example of a TI. So we stumbled upon working on bismuth bilayers when we were, for other experiments, we were studying the properties of bismuth when crystals. So if you take a crystal of bismuth and look at it and think about the 1-1-1 direction, actually it looks like stacks of bilayers on top of one another. And in fact, if you cleave such a crystal, you will get step edges, which have exactly a bilayer height. So these are just stacks of many bilayers on top of one another. So it's not a bismuth bilayer in isolation, but with these experiments, even on bulk bismuth with these bilayer islands, as I would call it, we found evidence that there is residual presence of these edge modes living in this system, which is living on top of a metal, if you wish. And the evidence for this 1D edge modes would show up in tunneling spectroscopy at the edges. You see this sort of in spectroscopy, the Van Hoos singularity of a 1D channel. And then we did a number of experiments, which I'll show you later in this talk, where we actually studied the scattering properties of these edge modes to show that they don't have any backscattering in this normal way of typical, edge modes, trivial ones. And I'll show you that they're actually quite sensitive to magnetism as well. And that provides us a way to show that they are topological. So there's also an added interest in bismuth, which is going on, which is that these states may not be, when you make a three-dimensional sample, it might actually be part of another class of materials called higher order topological insulators. So higher order topological insulators, in this case, the sample is a semi-metal, but the concept is can be carried over to semi-metals, is they have properties in which if you cut the material, in a bulk form, three-dimensional form, there will be these hinge states, which characterize the properties of the edges of the crystal. And these hinge states follow a very unusual pattern having to do with the gaps that you introduce in the, it's sort of like crystalline topological insulator, between faces of crystal, two faces of the same crystal. So this also shows something that people have been thinking about in terms of bismuth. And I'll show you, we have some data that suggests this to be also relevant to bismuth that we are, bismuth, the edges that we are studying. So let me, let me go over this. Yeah, so yeah. So that actually here's the data that shows this connection to the hinge mode idea. So if you look at the bismuth bilayers on bismuth, these sort of islands or dips in them or holes, what you find is that this edge mode that shows up in tunneling spectroscopy as, let me go back, as this sharp Van Hoff singularity in the tunneling density of states, this edge mode does not appear on all edges if you have a hexagonal shape divot or an island. And what's interesting about this is that, you know, it's very hard to do realistic bulk calculation here. But what it looks like is happening is that if you take a sort of tight binding model of bismuth and think about, you know, the states at some edges are very strongly hybridized with the bulk, this will produce effects that look very much like the sort of the hinge states that people expect bismuth to have. Now, so the main thing is to talk about these edge modes and to talk about superconductivity and how magnetism modifies these edge modes and whether we can use them to realize a Majorana zero mode. So the way to do that, to introduce superconductivity into the system, is of course has to be done through a proximity effect. And the way we did this is we used very thin layers of bismuth grown in situ. These are samples with seven or so bilayers of bismuth stacked on top of one another, on top of niobium 110. And what's nice about this is that when you grow this system, it actually looks like it's basically appears as a bismuth 111 surface of a crystal. Because you know you're looking at exactly this surface, even if it's a thin film, it's epitaxially grown. And when you look at these thin films, we basically see everything what we have seen for the edge modes that we saw on the bulk bismuth samples. First, we see that the edge modes appear on what we call A edges, and do not appear as B edges. These two edges are actually different. In structure, we can distinguish them. They go along different orientation relative to the underlying crystal. And this is the idea that the fact that they appear here and do not appear here is the idea that they might be going into the sample at this point is what people think about as evidence for hinge-like properties of these states. Or it could be that this is a 2D TI, and we know the structure here at the B location is different than A, and it could be that the edge modes here are very strongly hybridized with the substrate underneath. The way to think about these edges being different, let me go to the previous slide, it can be illustrated if you look at this sort of the atoms in this plot I have here. So bismuth has a zigzag structure. So the A edges are the ones where the last atom are up away from the sort of the step on the surface underneath, and B edges are the ones that are terminated at the blue atom, in which that atom is very close to the substrate underneath. So these two, both this idea of hinge mode and both this idea of hinge mode and the hybridization of a 2D TI edge mode with the substrate underneath can explain this experimental result. So regardless of those two different explanations for these results, we can also show evidence, I'll show you in a minute, where of the topological properties of this edge mode by their sensitivity to magnetism. But before we get there, let me show you, for example, here comes how we probe their sensitivity to magnetism. So we can take an edge, which is a region which is fairly straight, and we can measure the density of state along this edge, okay, as a function of position and as a function of energy. And you can see that there is some interference pattern that arises because of the presence of a finite edge in this system. And the interference patterns that arises here relates to the presence of the sort of two bands, if you like, crossing, the different crossing of the chemical potential for this edge mode, even in the calculation. And the main point I want to bring out here is that from these measurements, we know that there is this one-dimensional state, which is living right at the chemical potential here from the FFT of these real space maps. And we can see that if you, so that experiment was done when you applied a little bit of field to drive the niobium underneath normal. And then when you remove that magnetic field, you see that this one-dimensional state is getting proximatized. So in these measurements, you get a gap in the density of state. This is a superconducting gap. And what's nice about this is that because the substrate is very, very thin, the film is very, very thin, very close to the substrate, the superconductivity from the niobium has basically leaked in very nicely, and the gap, the proximity gap on these edge states is exactly the same as what we measure on the niobium before we put the bismuth on top. Okay, so now we add magnetism. So how do we add magnetism? So remember, we need to add magnetism to cut these topological edge modes to introduce a different kinds of gap underneath, which gives rise to also backscattering of these edge modes from the magnetism. So the way we do this is after we are done growing the bismuth on top of niobium in the same machine, we can evaporate iron onto the surface and at very, very low quantities, and then anneal the surface to form iron clusters. And not surprisingly, the irons like to cluster at step edges, right? And we use these small clusters as a way of trying to introduce magnetism on the surface and on these edge states. So first, I'll show you that these clusters, which very nicely go to the edges where the one-dimensional edge modes are magnetic. And again, we use spin polarized STM. And then we can polarize the STM tip in different directions. For these experiments, we use these tips that it takes very little field to switch them. Okay, so you're looking at the switching property of the tip with very, very small fields. They just jump, okay? And the clusters here do not jump up to fields of 1 Tesla because of the very strong crystalline anisotropy that they have living at this location. Now, what you see in these jumps is basically it's giving you information about the spin polarization of whatever site you're making this measurement on. And you can see that the jumps basically change as you move from location to location on the sample. And here at this location, there is no jump at all. And the polarization basically is related to the size of this jump. So if you make these measurements as a function of position relative to this cluster, for example, shown here, and plot basically the size of this jump as a function of position, you see a very nice sort of oscillatory behavior, which appears to be from the RKKY spin polarization that's created by this cluster on this surface, which not only, of course, affects areas away from the surface, but also affects the edge state, which we are probing. We can also see evidence for the introduction of backscattering on these edge modes. So here is, again, a topograph. It shows these iron clustering on 2 edges of 1 long edge. You can also measure, before you evaporate iron, you can do a similar experiment on the same surface without these edges, without these clusters. There's still an edge there, which is where the edge mode goes. And there is scattering that happens between the edges with and without iron. Without the iron, those scattering has to happen in the same spin channel. And you can analyze these interference patterns using Fourier transform. And you can observe there is a branch of the scattering which takes electron from the same spin channel to the other one. In this case, the crossing there are two crossings. Actually, there are two Q vectors there are 2 points that are connected with the same spin property in the material. It's not a backscattering. It's like a weird forward scattering that you see when you have no magnetism. But when we put the magnetism in, you see additional scattering that comes from these iron clusters being there. And it's this wave vector that relates to the presence of backscattering because of the presence of the iron there. Okay. So we can also, there are other experiments which I can show you if there was time, which we can see how these iron clusters modify the properties of the edge state underneath them. But although you can imagine we are very sensitive to the properties of the iron cluster when you're doing STM experiments on top of them. So it's very difficult to directly measure the gap there, but it does leave some signatures which I can get into if there were questions about how you see evidence of the gap in the STM measurements. But turning back to the Majorana, so we have here superconductivity along this edge. There is a gap. We have the magnetic clusters introduced. And then we can now take measurements as we bring a tip approaching the cluster from the edge mode. And what you see here is that when you're approaching the cluster, the magnetism of this thing sort of is around, and it does leak into the part where superconductivity is strong. But this magnetism is not strong enough to kill superconductivity here, so you see a gap. On the other side, you can still see some evidence of superconductivity, and it actually looks like you have in-gap states produced by the cluster. Remember, this whole thing has become a surface. It's superconducting, even underneath the iron cluster. And what's interesting is right at the edge of these two regions, between where the cluster, just at the corner, before you climb onto the cluster, you see a clear zero bias peak. And this zero bias peak, again, it comes from, it appears very localized in a very small region of space. And here on the other side, you also see a zero bias peak on this cluster. But this behavior is, this cluster has other in-gap states that have larger values closer to zero, which at this temperature makes the measurement sort of have some signals from other states nearby. So this is a zero bias peak that we're looking for. And this zero bias peak, if you plot its magnitude as a function of position, you'll see that its magnitude is not on the cluster, and it's exactly on the edge as you approach the cluster. Here's the topography and the zero bias signal plotted on top of one another. What's more is that if you go onto the edges which are where this edge mode is not there at all, which you cannot see it in the experiment, and repeat similar experiments on many different clusters, we never see a zero bias peak develop there. It looks like there is magnetism, of course, from the cluster creating in-gap state, but for all the measurements we have done, you never see a zero bias peak created at the boundaries of the B edge, where this edge mode is no longer there, basically with the magnetic cluster being present. And we know the edge mode is either not there or highly hybridized because of the absence of in the spectra, this Van Hoff singularity of the edge state is completely gone along these B edges. Okay, so that's a control experiment. The other experiment, which we have some results from, is a control experiment with the question of magnetism. So remember, I mentioned that we have, depending on the orientation of this magnetic perturbation, sometimes you would have the Majorana if you would only have the Majorana if there are magnetization has a component that's perpendicular to this edge mode. And if it's parallel to this edge mode, it disappears. So how do we get information about the magnetization direction of the cluster? Well, we turn back to our spin polarized tip, which we can polarize with a small field, as I showed you, in different orientation. And this field is small enough that the clusters do not seem to switch. Otherwise, you would see tunneling switching between two magnets, which we do not observe as we sweep up to this field. And what you find here is the height difference. Again, we discussed this with respect to chains. When you polarize the tip in different orientation, the STM tunneling current depends on the relative orientation of the magnetization of the tip and the sample, and it would appear at different heights. But now we can polarize the tip in different XYZ direction and measure the height of the island, from which we can extract an effective magnetization orientation between the tip and the sample. And what's interesting is we can go to different clusters, and so the orientation here is relative to XYZ axis, which has dialed in with the magnetic field. So between different clusters, we can measure what component of the magnetization, what the component of the magnetization is doing in XYZ between the different clusters. And we see that they are changing, okay? So this is changing relative to the direction of the edge state, which also the momentum of the edge state determines the spin orientation of the edge mode, which would be perpendicular to it, but it could be along a direction which we do not know experimentally. So what the experimental observation we have found is that we go around and look at many, many clusters, okay? And we basically find clusters of sort of two types. So there is the XYZ orientation with the X direction along the edge, Z perpendicular to edge, and Y perpendicular to it. So we see when the Y component of the edge state has what we see here is that there are some distinction between what I call red and the blue curves here. These are the red clusters show Majorana zero mode, and the blue clusters that seem to have equal orientation in X, Y, and Z do not show Majorana zero mode in our experiments. So we believe this is consistent with our experiments. So here's an example of a cluster that's magnetic. You can see that it introduces in-gap states, but when we go and measure as a function of position near such clusters, we just don't see a zero mode, even though it's on the right edge. So we believe this contrast, I believe this contrast has to do with the orientation of how the presence of this magnetic orientation modifies the gap that it produces on the edge state. So we can't measure directly the band structure of these edge states, but what we have found is that if we model them, so this is a bilayer bismuth band structure, and this is what the edge state band structure will look like if you gap it with just the magnetization, which is along the X direction. And if you put the magnetization along the Y direction, you see that this hybridization gap depends on the orientation of the tip, okay? And we believe that this difference may be responsible for the presence and absence of the Majorana, because as you can see, the difference between these two is that the gap at zero energy is going away. It's actually shifting in this very anisotropic fashion, depending on the orientation of the tip, orientation of this magnetic cluster, and the spin orientation of the edge modes, which are these are things that are very difficult to measure. But again, we don't have up to here, we have a measurement which is consistent with the presence of a Majorana zero mode. Now the question is, can you distinguish that this is not the trivial state that has emerged because you've just gotten unlucky? So again, we go back to our spin signature of the zero mode, which is, as we discussed in the first part, in our chain experiments, really helped us out to show signatures that are just look like we can distinguish the Majorana zero modes using them. So again, here we go back and do the same kind of measurements, and we are doing polarization measurements on the cluster. So the cluster is magnetic, introduces magnetic states in the gap. We have seen them as peaks. They produce this asymmetric signal in the spin polarized STM measurements for reasons that I told you before. And again, you find the zero mode in the middle of this experiment, and in the middle of this, between the cluster's edge and the continuation of the edge. And we see a very large polarization of the zero mode in this experiment. So we believe that this is also a good test here, and it looks like it gives us the same result, which is that the Shiba states have this anisotropic behavior, and the in-gap states, the zero energy states, does not get canceled out in this STM measure. We also noticed something kind of peculiar. So remember, the polarization here is measured relative to the tip orientation. So with the same tip, we measure the polarization of the cluster, okay? And then we measure the polarization of the state at the end. And what we find several times, which is very intriguing, is that we find them to show almost opposite signals to one another. So this one is up and this one is down. Whereas in the chain experiments we did, the chain magnetization, remember that plot I showed you with the band structure, the chain magnetization that determines the crossing of that band gives Majorana its spin orientation. In our model calculation, that's what we see. Here in this problem, the cluster is just cutting the one-dimensional edge mode. And the spin polarization of the Majorana is actually not coming from the cluster at all, okay? So there, the peak that we measured for Majorana and the peak we measured for the magnetization from the chain had the same, if you like, sign. So if this was up, this would be up. If this was down, this would be in the other direction down. Here is the opposite. And so we started thinking, is this an accident? And so this is what I was showing you before for the chain model. See, this is up and the Majorana is up. If I flip this down, which comes from the magnetic orientation of this, the Majorana spin would turn the other direction. And this is the difference that I was talking about. Now, we've done some toy model calculation, which tells us that the orientation here of the Majorana in this problem is actually quite different than the chain problem. What it looks like is that if you have, let's say, your spin of one-dimensional edge states oriented as I've shown in this slide, so of course to open up a gap along them, the biggest gap you would get is if the polarization of the cluster is basically perpendicular to it along the direction of the chain. So this is kind of like nanowires, which is why you apply the field parallel to the nanowires. Okay, you can think of it that way. This is why it's opening up a gap there. So the Majorana spin here is determined both by this spin direction and the direction of the gap that you have introduced. It's actually like a tripod that actually points in a different direction completely. And this has been actually calculated by several theoretical colleagues before our experiment in the nanowire context. So we believe that this difference here has to do with the fact that this state at zero energy is pointing, let's say, up, and the cluster, which is creating the in-gap state that we measure here, is pointing in an entirely different direction, which is what determines the contrast between these signals that we see in the experiment. So we'd like to say that this makes even a stronger case Because not only this polarization does not go away when you do this spin polarized measurement of this zero energy state, which should cancel it out if it's trivial, but also its value being different, or in a different direction, gives us some feeling that we might be actually dealing with a state which is oriented in a completely different direction. The details of this, of course, depends on the details of the spin-orbit coupling that creates these states, and we haven't done any of that detailed calculation.
Ali, just to let you know, 15 minutes to
I'm almost done, so we can have questions in a minute.
Perfect.
So I'm just summarize. So in this system, the signatures of Majorana are the zero mode and their sensitivity to the magnetic orientation of the cluster, and the spin polarized measurement that I just showed. And I think that now this brings me to the end of the talk. So I talked about basically these two platforms, and the advantage of these platforms, in trying to explore Majorana physics, is that you can see what you're doing. You have all the different structural and magnetic and superconducting spatially resolved information to put together to see whether you're consistent with what you measure. Of course, we haven't gone to the point of trying to manipulate Majorana besides this simple experiment so far, but that's the direction we are headed in different directions in these different platforms using our tools. So these are kind of things I told you about. So thank you for your attention. So I'll stop here and leave it for questions.
Well, thank you very much, Ali. I have to provide you some cheering.
That's good.
And there is a question here. Let me just stop this now. There is a question by Ingrid Zimmerman, who in previous talks was not Ingrid Zimmerman. So can you open your mic and ask, please?
Yeah, so can you show the view graph again where you have the clusters magnetized in different orientations, X, Y, and Z?
Mm-hmm.
And then you have something like the amplitude. I didn't quite get what is that amplitude and then the outcome.
Yeah, thank you. So perhaps I wasn't clear. So you measure the height of the tip. I think I'm sorry, I'm driving backwards. You measure the height of the tip with the, you measure the height of the island with the tip polarized in different orientation. So this is just what it's how high the cluster appears above a non-magnetic surface, which in this case is the bismuth surface. So you see this is high, this is about the same, this is high, okay? And then you can think of this as a three-dimensional vector, okay? And from that, you can try to construct, from that, you can try to construct this magnetic, the components of the magnetization of your cluster, okay? So this cluster 1, cluster 2, 3, 4, these are the different numbers, and these ones have high X. So the contrast is very large when you polarize the tip in the X direction. These are very low contrast in the Y direction. These two have very high, and these are all about the same in the Z direction, okay?
I see, so that MX, MY, and MZ is measuring the magnetic component of the cluster, but you measure by polarizing the tip in that direction. Is that what you're doing?
Yes. Because as you magnetize the tip, you could of course affect the cluster as well, but the clusters don't switch at all.
Right, you have a different coercive field.
Exactly. So that's what we're doing. It's only half a Tesla, so they seem to be stable. Otherwise, you see switching, which you see on other islands. Now, if you put that in our model of these states, we see the following behavior. If you have large MX is along the edge. You have this beautiful gap, okay?
Right.
And if you crank up my, it starts to modify the gap,
Right.
okay? And it is still somewhat there, but you know, it's not at the Fermi energy. And we believe that this is changing things. And I can, since there is a question about this, let me see if I can show another data that I had in my backup, if I find it. So we think we have some evidence of these gaps. This is kind of the gap. This is when it's gapped, okay? We have some evidence of these gaps from kind of the Van Hoos singularities that we see, not Van Hoos, from the spectra. So we suppress superconductivity completely. And we see these very, very large, we go on the iron cluster, we see these very large sort of sudden changes that's happening near the zero energy. And we believe this relates to these states gapping the edge states, this, you know, because of the large density of states. But yeah, so this seems to correlate with the presence or absence of the zero bias peak. What would be nice is to get clusters that have small coercive field, and you can flip them in the experiment. That we haven't done.
I see. So what you're saying is that depending on the orientation of the magnetic cluster, so the magnetic orientation of the magnetic cluster, there's either presence or absence of the zero bias peak.
Yeah, that's an experimental observation.
I see. Okay, great. Thank you.
Thank you. We have another question from Yang Zhengao. You can open your mic and go on.
I can't hear you.
His mic is still, I can ask the question.
Okay.
Or, yeah, he seems to have problem. So have you probed any Kondo and spin flip signature? And are there any competition between Kondo, Shiba, MZM, and spin flip?
Yeah, okay. So typically Kondo effect would happen if you have screening of your magnetic moment, right? So so first of all, here we are not talking about doing single spins in these experiments. Many of them are clusters. And typically we also use magnets with large magnetic moments. So in that situation, the Kondo temperature is less than the superconducting transition temperature. So you do not, you do not see a Kondo effect to turn on. So you can turn off superconductivity with a very weak field. I mean, early on, for example, the question was whether what we were seeing the zero bias peak were Kondo peaks and whether you could split them. And we have done experiments, which I don't have the slides for because we've done it many years ago on many of these systems. And these systems, the spin is so large, the Kondo physics is not really relevant anymore. Does that answer the question?
Anybody has another question? You can open your mic or type in the chat.
Let's see here.
While they're thinking, Alia, I have a little bit of a knot in my mind trying to understand what's the origin of the Majorana fermion in the superconducting ferromagnetic chain. Okay, so if I understand well, when you have the competition between superconducting and magnetic and the ferromagnetism, electrons sort out the spin and superconductivity in pairs so that it's fine. And then there would be at the end of the chains unpaired electrons that would take the properties of the Majorana fermion. Is that right?
Well, I'm not sure. So, I mean, the way to think about it is there are sort of two ways to think about this problem. One is to think about the chain as a one-dimensional system, which has its band structure, okay? And then you can ask, well, can this one-dimensional system be superconducting? Become superconducting. So one is to look at it from the perspective of the chain. The other is to look at it from the perspective of the superconductor. So from the perspective of the chain, it's very easy to understand that if you have such a band structure, this is for a one-dimensional system, and if there was large enough spin splitting, okay, you need an odd number of bands, okay, so that you have one left over.
Yeah.
Then it's always topological.
Okay.
And now the question you can argue about is, well, how large is that gap? Well, the gap can be very small compared to your original gap if alpha is very small compared to J. Now, you can take a different perspective, which is to think about the superconductor and think about the magnetic atoms as a perturbation. So you put one magnetic atom, what do you get? You get one of these Shiba states. So let me go back here. I mean, right? So it's like, for example, here, you get one of these Shiba states. So forget that how we are plotting it, but this is state inside the gap, right? Let me go back just a moment. This guy. You have one impurity, okay? That gives you one state. Now imagine I add more impurities, but the impurities are not too close to one another. They're sort of far apart such that these states in the gap overlap with one another. Does that make sense?
Okay, no, I see. I see.
And this becomes a band.
Yeah.
Now, it turns out if you look theoretically, once these two bands cross each other at zero, the system becomes topological.
Yeah, okay. All right, thank you. Anybody else with a question to Ali? You can raise your hand, open your mic, or type in the chat. And if not, I should give
right on time.
Right on time, that's wonderful. Mark, do you have any statement to make? Any?
Mark is gone to sleep.
Yes,
No.
sorry.
So do you have any final announcements to make?
Wisdom? No.
Okay.
Except that we'll all reconvene tomorrow at 10, usual time.
10 or 10:30?
No, 10. Come on. It doesn't matter. You won't be up.
Oh, right. Okay. I'm talking about my time.
What do you know, Mark? Maybe he will still be up.
Yes, of course. Yeah, but no.
It's not that far from when I get up usually.
Okay, all right.
Okay.
Very good.
So I will see you guys tomorrow.
Yeah, so thank you very much. Thank you very much. I'll give you some more analog clapping now.
Thank you. Thank you,
Thank you very much for this very nice talk. And we'll have the other section of lecture by Ali tomorrow. And thank you very much.
Take care.